Hey, welcome! Today, we're going to tackle a really powerful but, yeah, sometimes pretty complex database model, the Distributed Object Database. We're going to break down exactly what they are, how they work, and most importantly, why they're such a big deal for handling the kind of messy, complex data we see in the real world. All right, let's jump right in.
So, to get us started, I want you to just think about this question for a second. For ages, we've organized data in these nice, neat rows and columns, basically a giant spreadsheet. But what happens when your data isn't that simple? What if it's got all these complex relationships, its own behaviors? What if it's more like a living, breathing world? Well, that's exactly the kind of world that object databases were designed for.
And this right here is the fundamental shift in thinking. The relational model, which most of us have probably worked with, it keeps data in these flat, separate tables. The object model, though, it does something totally different. It bundles the data and the things you can do with that data, its behavior, into one single package we call an object. It's kind of like the difference between getting a list of car parts versus getting an actual working car that you can drive.
Okay, so how does the system tell one object from another? This is where a crucial concept called object identity comes in. You see, in a relational database, if you have two rows with the exact same info, they could be seen as duplicates. But in the real world, that's not always true. The source material has this fantastic example. Think about two parents, Peter and Susan. Each of them has a child named John, who's 15 years old. The question is, are they parents of the same kid, or are there two different kids who just happen to have the same name and age? An object identifier, or OID, solves this ambiguity. It gives every single object a unique ID, like a digital fingerprint, so the system knows with absolute certainty if we're talking about one John or two.
This brings us to the next logical question. How are these objects actually built? They don't just pop up out of nowhere. No, they're constructed from a very specific set of blueprints using these two core ideas, classes and inheritance. So every object you create is what we call an instance of a class. And you can honestly think of a class as a blueprint. It's perfect. If you're building a house, the blueprint lays out the structure, how many rooms, where the windows go. A class does the exact same thing for an object. It defines the shared structure and the behaviors for every single object of that particular type. And every one of these blueprints has two main components. First, you've got attributes. These are just the properties, the data points that describe the object. So for our car class, that'd be its model, the year it was made, its color. Then you have methods. These are the behaviors, the actions the object can actually perform. So a car object might have a method to calculate its age, or another one to replace a tire. See? The data and the actions all live together in one place. Now this is where things get really, really powerful. Object models use this concept called inheritance. What it means is, instead of building a new blueprint from scratch every single time, you can create a new, more specialized class that just inherits all the properties of a more general one. It saves a ton of work, and it creates this really clean, logical structure for your data. Let's just walk through this example right here. Say you start with a really general vehicle class. It's got attributes that all vehicles have, right? Like an engine, a make, a model. Now you need to define a car. Well, instead of starting over, you just say that the car class is a subclass of vehicle. Boom. It instantly gets all those vehicle properties. Then you can add the attributes that are specific only to cars, like bumpers and tires. You've just reused a general blueprint to create a much more specific one. It's super efficient. So, we've got these incredibly powerful objects. But in the modern world, data almost never lives in just one place, does it? It's spread out everywhere. And this is where that distributed part of the name really comes into play. Let's dig into why this is so critical. Let's use another really good example from the source material to make this concrete. Imagine a big engineering firm. They've got offices all over the globe. Boston, Waterloo, Paris, San Francisco. They've got projects and employees in every single one of those sites. And all of that information needs to work together like it's one single cohesive system. And that's the multi-million-dollar question, isn't it? This is the core problem that distributed databases are designed to solve. You can't just stick the whole database in Paris and make the team in San Francisco wait for every little piece of data to travel across the ocean. That latency would be a killer. The system has to be smarter. It has to feel local, even when it's global. The key strategy for pulling this off is something called fragmentation. Now, the name sounds a little technical, but the idea is actually super intuitive. You take your data and you break it up into logical chunks, or fragments. Then, you can store those fragments at the locations where they're actually used the most. This slashes network delays and gives you a massive performance boost.
And this slide shows a classic way to do it, called horizontal partitioning. We've got a table of projects, right, the proj table. Instead of storing the whole thing at one site, we split it horizontally, by the rows. So in this case, all the projects located in North America get stored on a server over there, while the European projects are stored in Paris. The data is physically separate, but to the application, it still looks like one big unified table. And now, as you can probably guess, managing all these objects spread across a global network, well, it comes with its own unique set of challenges. So let's look at two of the biggest ones: how you store this stuff and how you clean it up.
In an object database, objects are being created all the time. They're being used, referenced, and then eventually they're not needed anymore. But if those old, unused objects just hang around, they start to clog up the system's memory, slowing everything down. The process of automatically finding and deleting these obsolete objects is called garbage collection, and it is absolutely essential to keeping the whole system healthy and performant. And there are two main schools of thought on how to do this. First up is reference counting. This is kind of like a popularity contest. Every object keeps a running tally of how many other objects are pointing to it. The second its reference count drops to 0, poof, it's deleted instantly. It's fast, but it can get tripped up by complex loops. The other approach is tracing-based. Here, the system periodically starts from a known route and basically plays detective, following every reference to see which objects are still reachable. Anything it can't find is considered garbage. This method is more robust, but it can cause the whole system to pause for a moment while it does its thing. A classic tracing algorithm you'll hear about is mark and sweep, and it works in two really simple phases. First, you have the mark phase. The system just goes on an exploration, following every link it can find and marking every object it reaches as live. Then comes the sweep phase. The system scans through all the memory and just sweeps away anything that didn't get a mark. It's a really effective way to clean house.
Okay, phew. We've talked about objects, inheritance, distribution, cleanup, the whole shebang. So let's zoom out. What's the big picture here? What's the real payoff for going through all this?
This comparison table is super helpful for understanding the landscape. It pits a pure object-oriented database, an OODBMS, against an object relational database, or ORDBMS. And here's the absolute key difference. A pure OODBMS is built from the ground up to think in terms of objects, just like modern programming languages like C++ or Java do. This gets rid of that awkward translation step of trying to flatten a complex object into a simple table, which can be a huge performance bottleneck. An ORDBMS, on the other hand, is more of a hybrid. It's a traditional relational database that's had object-oriented features bolted on top, extending the familiar world of SQL. And that really brings us to the final question, the one to chew on. The data we create every single day, from our social networks to scientific discoveries to massive engineering projects, it's all getting more and more complex, more interconnected. The rigid structure of tables served us well for a long, long time. But as we try to model these increasingly complex systems, you have to wonder, is the future of data built on those simple, flat tables or on these dynamic, living objects? Something to think about. That's all for this explainer.